So in today's class, unfortunately, there are going to be a lot of equations, but I would like to talk about the physics behind the equations, and we will use these equations in next class to run the simulations and to trim the aircraft and so on. But before I begin, I just want to show you uh, a couple of important videos that I have added link to. And I would strongly recommend that you watch these videos before you come to next class. So let me show you where these videos are. So if you go to our class website on Canvas, please note I have added uh, some videos in chapter 5. So the first series is on the state space models. So these are the models we will talk about a little bit later in today's class. But there is a video on trim 1 and trim 2. So these two videos will give you a visual understanding of what exactly trimming is. How do we do linearization? And how is this linearization actually used in practice? Let me tell you, when you go to industry, you will notice many times the complicated nonlinear controllers are not used. What they do is they use something called as a linear approximation, a regional linear approximation, and then use something called as gain scheduling. So my recommendation to you is please take a look at these videos, trim 1 and trim 2, and then come prepared for the next class. That will save us a lot of time. So I can directly go to the simulations. And these are very nicely made. So I'm sure you'll enjoy it. Okay, so let's quickly recap what we talked about in last class. And the reason I want to emphasize on this discussion, because this discussion is going to be repeated for different set of equations again and again. So here is what we started with. We started with one of the equations from the 12 state equations. And if you recollect everything, this is the Genesis block. If you study blockchain, the first block is called the Genesis block. So this is the Genesis block, and everything stems from this block. So these are the first order equations that we are going to manipulate and come up with the control algorithms. So if you recollect, we started with the lateral equations. So we looked at the equation of phi, and in this equation, please understand, this is nonlinear part. And why is this a nonlinear part? Because this is product of transcendental equations, sine phi tan theta, cosine phi tan theta. So this is the nonlinear part. What I'm going to do is I'm going to describe this nonlinear part as a disturbance. That is something that is not needed. So then this equation will be differentiated. And when I differentiate this equation, please notice I'm going to get a phi double dot and I'm going to get p dot. But as soon as I get p dot, this equation for p dot can be substituted in this equation. And when that happens, all of a sudden, I get these control variables, delta R, delta A. So these control variables pop up, which means now I have means to control the system dynamics. And this process is going to get repeated again and again for set of lateral dynamics equation, longitudinal dynamics equation, and so on. So this is the process that we talked about in last class. So what we are going to do is, at the end, I want you to understand, all said and done, we had a roll instability, say roll disturbance, and we can control that roll disturbance by means of aileron deflection. And essentially the aileron deflections will ensure that the eigenvalues of this differential equation have the negative real parts, and that's why the system again after the disturbance goes back to its original state. Now, moving on, there is another aspect of lateral transfer function that is related to the course. And if you recollect what the course is, you will study that you have an aircraft. Aircraft has certain dynamics, and then you have the ground path. So we talked about the course angle and flight path angle. Course angle is the angle between the tangent and so this is called as chi, and then the flight path angle is called gamma. So what we want to do is we want to talk about the dynamics of chi with this lateral transfer function. So please understand, we spend negative real part means it's continuous time. Yes, negative real part means if you have an equation x dot is equal to ax, eigenvalues of a are negative real part, which means the system response is sort of asymptotic. Now, what we are going to talk about is we spent some time on coordinated turn. So in the last class, we talked about coordinated turn. This is what we talked about. Please understand, the aircraft never turns at the location. It does not have the ability to turn at its location. Whenever aircraft turns, it kind of rolls, it kind of bangs. And that is what is called as the coordinated turn. So what we are going to look at is we are going to look at the relationship between chi dot and then the roll angle. So we looked at the coordinated turn condition in last lesson. And then what we did is we subtract on both sides g over v phi. So please note we are subtracting phi. And the reason for this manipulation is as soon as I say tan phi minus phi, this approximation is nothing but d chi, which means now I have a derivative equation chi dot, and this is an important mathematical manipulation. Please note this mathematical juggling is needed so that we can come up with a differential equation that is sort of in a form that can be controlled using the linear technique. So once again, please understand the initial equation for the coordinated turn is chi dot is equal to g over va tan phi, where g is the gravity, va is the airspeed, phi is the roll angle, and chi dot is nothing but the rate of change of course angle. And if you are really looking at this to remind ourselves, this is the coordinated turn that we are looking at. So if you have any questions about terminology, just take a look at the coordinated turn slide. Now what's going to happen here is this simple manipulation allows me to substitute tan phi minus phi as d chi. So now I have a differential equation. Please note, this is the first order differential equation where I have chi dot on the left hand side and d chi on the other side. Now what it means is this first order differential equation can be expressed as a transfer function. So I will take Laplace transform of output divided by Laplace transform of input, and I can write that as a transfer function. And observe, once I do all that, this differential equation gets converted into a very nice algebraic equation. And some of you may ask me, like, why is this jugglery needed? And is this jugglery really needed? To answer to that question is no. If you can deal with the original nonlinear equations in state space dynamics, you don't have to deal with this. But sometimes the linear approximation is preferred because it's easier, it's quicker, and then it will give you a good insight into the eigenvalues and the system behavior. So what we are trying to do is we are trying to come up with a linear approximation to this complicated, super complicated nonlinear equation. Now, again, I want you to observe that if you look at the block diagram representation of this equation, if you look at the block diagram representation of this equation, I'm going to say this is the output. So as you can see, this output is denoted over here. Then what you have is you have the dx, which is actually treated as disturbance. So this is treated as disturbance. Now, what you have is you have P, which is the body rate that is integrated to get the value of phi. And that phi is added with the d chi, and that is fed into this equation. So I want you to understand, and please pay attention to the arrows that I'm showing. This guy comes from here. This guy comes from here. And as you can see, this is the transfer function that is represented in this block. And now this A phi2 divided by S A phi1 is the roll dynamics that we studied over here. So now what we are doing is the output of this block, is getting fed into the next part of the lateral dynamics. And this is a very simple linear approximation. Now, a step back, this d phi2 is also treated as a disturbance. So this is the disturbance. But dA, delta A, this is the deflection of aileron. Deflection. It is a control input. So you have, this is the input. So please note, this is the input, this is the output, and this is a very classic linear transfer function that we studied in Robotics 1, wherein you have an input and you have a transfer function. That transfer function takes the input, and transfer function covers changes input into output. Now, can someone tell me what type of transfer function is this? Is this an open loop transfer function or the closed loop transfer function? So the question here is the lateral transfer function just I showed, which is the combination of roll dynamics and the course dynamics. Is it an open loop transfer function or a closed loop transfer function? Correct. This is an open loop transfer function because there is no feedback. This feedback is not present. And objective of control is to identify this feedback or come up with some sort of a PID controller, some sort of a controller mechanism. In other words, add a block over here, which is, I'm going to call it as C. C can be used as a compensator or a control. Use this controller block so that once you feed the error to this controller modifies the transfer function so that the system is stable. Understood what we are trying to do is we have come up with a very simple transfer function representation of the input to the output. And what we are going to do is clearly here is no direct link between the output and the input. We are going to add a feedback loop along with some sort of controller algorithm, maybe proportional integral, or PID type of algorithm, so that the transfer function, we change the poles of the transfer function. And that's all we are going to do in this lesson. Now, the story of lateral dynamics does not end here. There is one more important piece of lateral dynamics, which is the side slip. And side slip is basically the difference between the yaw and the actual heading that the aircraft is headed towards because of the wind loading. So what we are going to do is, so first and foremost, the way we control side slip is by means of a rudder input. So we will start with the same basic equation. So we are going to start is the V, which is the lateral velocity in the body direction in the body coordinates, is equal to VA, airspeed, multiplied by sine of beta, where beta is the side slip angle. And what I'm going to do is I'm going to differentiate this equation. This is exactly what we did earlier. Once you differentiate the equation, you got an equation for V dot. And why am I interested in equation for V dot? Because as soon as I have V dot, I can substitute this V dot with the equations of motion. I can go back to this Genesis block and grab this equation for V dot and substitute that in the side slip dynamics equation. So don't forget the Genesis block. Everywhere we are gonna come up with a mathematical jugglery so that we can integrate one of those 12 equations into our simulation. As soon as I do that, you can see that the left-hand side of this equation has been replaced with one of the differential equations from the Genesis block. Now it is interesting, all of a sudden, when I change this equation for V dot, I have this controller input. So I have aileron input and I have the rudder input. And then boom, I'm gonna continue with the same process that I did earlier, which means I will take this block and somehow convert it into a very simple linear transfer function. So how we do it is this. I'm gonna write the equation for the side slip dynamics, which is B dot. Please note, B dot is over here. I'm gonna write down the equation for side slip dynamics, B dot, as function of three different terms. This is one term, this is the second term, and this is the third term. And please, these are the constants which are defined over here. And once again, dB, which is treated as the disturbance. Now, some of you may ask me this question. We are always talking about this disturbance. Is that really a disturbance? To answer to that question is no, it's not really a disturbance, but it is an artifact of coupling in the differential equations. So for an example, if you think about it, a slight change in one state causes change in the other state. But when we are trying to come up with a linear approximation, that is not what we really want. We want everything to be clean and neat. That's why all these nonlinear, complicated cross terms are somehow we try to compensate and we treat those as disturbances. If you think about the term d beta, this d beta term is actually coming from the differential equations of motion. This is not a parasitic term. This term is present in the equation, but to handle it, what I'm trying to do is I'm trying to treat this term separately so that the effect of this coupling term can be studied along with the effect of control. So please understand, this is the input. And because of this input, this is something that we get because of the coupling. And you will notice that something like this happens all the time when you have a system dynamics that comprises of nonlinear term, coupling terms, some parasitic effects. All those terms are treated as disturbance. And then you will come up with some controller algorithms or some sort of design techniques that would help you reject the disturbance. Now, what do I mean by rejecting this disturbance? So please try to understand. If you look at this equation very, very carefully, you would realize that this disturbance is actually product of multiple terms which are dependent on different states. Somehow I will come up with some sort of compensator design, some sort of a controller design, or some sort of input that would minimize or reduce this unwanted disturbance when I perform the simulation. Now, all said and done, how is this disturbance rejected in the actual physical system? And in the actual physical system, when you are trying to come up with some sort of disturbance rejection, essentially you would be adding some additional mechanical components or electrical components. I give you a very simple example. Imagine that you are walking and you don't want to feel the disturbance from the road. So the road is uneven and you don't want to feel the disturbance. So what you do is you change your insoles. You come up with, actually buy a better insoles that actually maybe have air cushion. So you increase the cushioning. And that is one way of minimizing the external disturbance. So that is actually a change in the physical system. Something like that can be achieved. Or if you are driving a car like a Mercedes Benz with air suspension, you can tune your suspension based on the amount of disturbance that you want to reject. So there could be some mechanical changes, there could be some electronics changes that you can incorporate in your system that would actually implement this disturbance rejection. Now we are going to perform the same mathematical operation. Once again, these equations may look big and long, but they are really not. So again, here is how we start. We start from the Genesis block. But since we are looking at the longitudinal transfer function, I start with the equation of theta dot. This is the same equation that we have in the Genesis block. So this is the second equation that I'm going to deal with. And now you know the drill. What I'm going to do is I'm going to differentiate the equation. As soon as I differentiate, I end up with a derivative of Q and derivative of R. And then I would substitute Q dot and R dot in that equation, and boom, I get the inputs. So let's do that. So this is how it is done. So what I'm going to do is once you do the differentiation, you have the theta dot, and then theta dot equation is differentiated into theta dot, and then the derivative terms are replaced, introduced, and finally, all said and done, what you have is you come up with a very nice linear equation that is shown over here. Yeah, the Genesis block called 12 equation. I call it the Genesis block because I was watching the blockchain videos, and then the first block that was created in the Bitcoin, the very first block that was mined is called the Genesis block. And since our first slide with all these equations is the genesis for whatever stuff we are doing in this lesson and again the next lesson. So when I say the Genesis block, please remember this is our Genesis block. So when I say equations from the Genesis block, that means these 12 first order equations. So what we are going to do is we will substitute that, and then you have again a very simple linear equation with the control input, but it is the elevator input. So now this equation can be represented as a very nice simple transfer function representation. This is a constant, this is constant, this is another constant, and this is disturbance. So the terms which are complicated, nonlinear, and the terms that sort of affect the linear behavior, those are called the disturbances. We want to minimize those. And here is a very simple transfer function. And once again, once you take the derivative, say theta dot in t, this is going to become s square theta of s. And then what you do is you take the Laplace transform of output divided by input. This is the output, and this is the input, and this is the disturbance. So now I have this nice transfer function representation. What this tells me is I have an elevator input. This elevator input is added to the disturbance, and the whole thing gets fed to this transfer function, and the output of this transfer function is nothing but the pitch angle variation. So this is the pitch angle. Now, next part of this is how do we approximate altitude, which is the height, from the pitch? And again, we have to go back to our Genesis block. So H is the third equation. This is the equation in the Genesis block. And now we will deal with this equation. We'll manipulate this equation to get a very nice controller representation. So H dot is equal to U sine theta, V sine phi cosine theta minus W cosine phi cosine theta. And again, this is represented as a very simple representation. Again, just as some input and then some disturbance. And then what we do is we just derive the transfer function associated with altitude using this. So now I have got an equation for H, which is based on the third equation in the set of 12 equations. So schematically, what is happening? You have the elevator input. Elevator input is acted upon by the disturbance that gets fed to the longitudinal transfer function that gives out a theta. That theta is acted upon by the external disturbance delta H, and that stuff, once you send it to this transfer function, this is the second transfer function, you get the height or altitude. So now what we have is we have a linear approximation to the complicated differential equations that we looked at. Now we are going to extend this to find airspeed. Now please note airspeed, once again, what airspeed is. If you have an aircraft, the aircraft is going to have velocity in 3 coordinates. It will have a velocity u, it will have a velocity w, and it will have a velocity v. So it's north, east, down coordinate. So the resultant sum total of these 3 velocities is going to give you VA when the wind speed, when wind is equal to 0. When wind is equal to 0, the vector sum of u, v, and w, vector sum of u, v, and w is going to give you the airspeed. And then what we do is, again, same trick, differentiate. And there is one easy trick that is done, which is not shown over here. We just do VA square is equal to U square plus V square plus W square. This becomes 2 VA dot is equal to 2 UU dot plus 2 VV dot plus 2 WW dot. And as soon as we have U dot, V dot, and W dot, we can actually use the differential equations on the Genesis block and then come up with an equation for VA dot. And this equation may sound complicated, but it is actually not. Because if you think about it, this equation gets written something like this, where you have U dot, W dot, and V dot. And these equations for u dot, v dot, and w dot come from the Genesis block. And once you substitute all that, you have this big equation that needs to be simplified. Again, don't be scared of these equations. These are the same equations that we used in our project 2 and project 3. But only thing what we are trying to do here is we are trying to come up with some simplification so that we can use linear control to control this state dynamics. Now, the next question is, now we have to find the trim. Trim, as we discussed, is an equilibrium condition. And in equilibrium condition, something like a level flight. And I strongly recommend that please watch the video that is linked onto the website. That will give you a very simple explanation of what trim is. Trim is nothing but determination of equilibrium. So please observe, and I will go through this in detail in next class when we trim this. After trimming, you are gonna get an approximation near the operating position. So for an example, this dynamics gets approximated and you get a trim equation, which is nothing but the linearized dynamics. So this is something after trimming. We get linearized dynamics near operating region. And this trimming is done so that the equations, nonlinear equations are sort of linearized. And we will talk about this trimming in detail, but once again, please watch the videos trim 1 and trim 2 on the canvas. And after this trimming is done, this is nothing but a representation in Jacobian. The trimming can be done multiple ways. You can actually perform trim analytically, or you can perform it numerically, or you can perform some approximate techniques, something called a fractional way of you actually take pieces of the equation and then or take those pieces of the block and then up with a linear approximation. So at the end of the day, all said and done, what will come out of trimming is a very simple linear representation of very complicated dynamics. So here is what's going to happen. You have this nonlinear system. X dot is equal to f of x comma u, where x are the states and u is the control input. So if you look at this equation, say for an example, delta E is the control input, and VA and other terms are the states. Now, what we do is when we trim, we consider the dynamics to be 0 and find out values of x and u, and then linearize about operating point. And once we do that, I would land up with an equation something like this. And this is, so A1, which is just a coefficient x plus B1 u. So A1 is a scalar, B1 is a scalar, or it could be a vector. So think about it, that I had this complicated nonlinear equation. After trimming, now I have this simple linear equation. So trimming is the process of simplification near the operating point. And that's all what we are going to do in next lesson. We will take super complicated nonlinear equations and we will use Simulink to perform numerical trimming. We'll start with some simple equations first, perform the trimming or linearization by hand, run that through sync, see if our answers are correct, and then begin with a complicated set of nonlinear equations given in on the genesis block and come up with the trim conditions. So all said and done, at the end of the day, this is what we get. So we have the equation for airspeed, and that equation for airspeed is defined in some terms of following inputs. So airspeed is the output, and airspeed input to the airspeed is the throttle. And then in addition to that, you have some pitch variation. This is pitch and our disturbance. And that comes from the equation that we looked over here. So finally, at the end of the day, just like the previous blocks, we have a block, there's an output, there's a transfer function, there's an input, and this input gets added to the disturbance and the additional variables. So this is overall transfer function approach. Now, what we have done in this part is simply we took these equations given on genesis block and expressed these equations as transfer functions. So we came up with a transfer function, excuse me, in the longitudinal direction, and we came up with a transfer function in the lateral direction. And what it means is, and please note, these transfer function representations were all open loop. So at the end of all this simplification, now what we have is, we have, please note, open loop transfer functions. And what we are going to do with these open loop transfer function is we are going to design the control loops. We will add some sort of feedback, and we will add some sort of a control, and system will be controlled. Sometimes the system will be controlled just with feedback. Sometimes if the feedback is not sufficient, then we need to add some sort of a controller block over here. That way the system will be controlled. Now, some of you may ask me, this sounds complicated. How do we do it? So to answer that question, how do we eat an elephant? So this is the question. How do we eat an elephant? And the answer to this question is in pieces. We are going to use, yes, we are going to use the same approach, which means if you look at the control, the transfer function, it's going to look at, this is going to look like super duper complicated transfer function. You're going to have disturbances, then you are going to have some interdependencies, then you are going to have some output. This output will get fed back somewhere over here, and then you are going to get, at the end of the day, you have certain inputs. You have input 1 acting on this block, you have input 2 acting on this block, maybe input 3 acting on this block. So basically, this is what open loop transfer function is going to look like. What we are going to do is, we are going to control successively. This is called as successive loop closure. And this is an important technique, successive loop closure. What does it mean? It means, first and foremost, I'm going to look at this block. And then I'm going to design a feedback controller that stabilizes this block. So once this block is stabilized, then I will look at the block that is outside. Then I will stabilize this block. Once this block is stabilized, I will look at the most outside block. And then I will successively close the loops on these blocks to make sure that the entire system is stable. But there is a problem here, because there's something that we have to consider is the bandwidth. Now, this may be difficult to appreciate, but please try to understand. So consider that you have an actuator over here. You have an actuator in the innermost loop. You have the actuator in the innermost loop, and that actuator is super slow, which means you want to control it, but that actuator doesn't move. So you want that actuator to move quickly so that this loop can be closed very quickly. This loop can be closed quickly, and then this loop can be closed, because you want the system to be successively closed. So if you do not have high bandwidth actuator in the innermost loop, this successive loop closure will not. In other words, you need the internal actuators, internal system to be super duper fast, outside system to be a little bit faster, and the outermost has to be sort of the slowest. So basically you start closing the loop from inward to outward just to make sure the entire system is completely closed. I just want to give you what would happen if the loops are not properly closed. Say for an example, you will try to provide an input on the throttle and then try to control pitch. You want your inner loop, say if it's a pitch control loop, to be closed first and the throttle control loop to be closed second, but throttle is acting faster than the pitch, which means your operating states for the inner loop will be suddenly changed, and you no longer would be able to effectively control the innermost loop. So we will talk about the successive loop closure. But if you look at the dynamics of unmanned vehicles, not the super complicated vehicles, they are used in aerobatic maneuvers. Usually the successive loop closure technique is fairly successful. So you can actually use this successive loop closure to control the system quite accurately. Now this finishes the discussion on the transfer function. So please understand, in this chapter, there are two things. One is a transfer function representation, and second is the state space representation. You can implement the control in the transfer function. You can implement the control in state space. When you are implementing the control in the transfer function, you have no other choice but to use a linear control technique. But when you are controlling in state space, potentially you can use a linear control or you can use a nonlinear control. So initially, I'm going to talk about the linear control in transfer function and linear control in state space. And subsequently, once we get more comfortable, we'll talk about the nonlinear control techniques. Next part of this lesson is talking about the space dynamics. But before I start discussing that, are there any questions on the transfer functions? So at the end of the transfer functions, we got all these blocks connected with each other. And these blocks are actually in the open loop. Now, what we want to do is we want to design the feedback loops and control each and every block step by step so that the overall dynamics can be controlled. That's the goal. So before I start state space, are there any questions? Next part is state space models. And the state space model, I don't have. Yeah, Alejandro, you have a question? Do you want me to unmute you? Alejandro, you are unmuted if you want to ask a question.
Yeah, so since we hadn't done these transforms, is this the next step on the project where it's gonna physically move the plane, up, down, north, or east?
I didn't understand. Oh, so right now, if you look at the plane simulation that we have done, okay, that simulation is not externally controlled. So it's like you have the manual input and you are controlling the plane. But if you look at the next project, and that project is coming here in the simulation project, you will notice that in the simulation project or the assignment that I have given, first we are going to find the trim conditions, and then we are going to come up with a controller, and then we will integrate our controller with the project 3. Does that make sense?
Yeah, so this trim transforms allows us to have a controller for the airplane.
Yeah, so think about it like you will specify. So here is what you might have observed in your simulations. So if you, there are, I don't know if you played with the simulation, you will notice that majority of the conditions, the plane is unstable. There are only few conditions that you can pinpoint from trial and error where the plane behaves the way you want it to behave. Do you agree with me?
Yes.
Now, what we are trying to do is we are trying to come up with some sort of algorithm or some sort of control law that would change the elevon and the thrust input. It will adjust the elevon and thrust input based on the roll, pitch, and yaw, based on the wind condition, so that the aircraft self stabilizes. What it means is, as long as our linear approximation is correct, as long as this aircraft is flying in a linear mode, that aircraft would be able to stabilize itself. And since this is a linear control, the domain of operation, which means where these controls are applicable, will be limited. But you'll be surprised that range is quite big. So what we will do in the subsequent project is we will design these control loops, and we will integrate these control loops in our simulation, so that we change value of VA. If you change the wind speed, if you change the wind gust parameter, the aircraft will be in stable level flight on its own. Does that make sense?
Yes.
Okay, Zubir has another question. Aren't the slider we adjusted controller? Yes, that observation is correct. But what we did was open loop control. We looked at the plane, and then we sort of guessed and tweaked, custom tuned our sliders so that the aircraft got into level flight. But in the next part of the project, we will develop a controller algorithm that will take the input or take the feedback from the aircraft state and self-stabilize the aircraft against the gust or the wind loading or maybe some other disturbance. Does that answer your question, Zubir? Okay. Any other questions before I begin further? I mean, before I start the state space part. Now, I don't have to spend a lot of time on this because the equations that are given on the Genesis block are the state space equations. So please notice these equations are the first order state space equations where there are 12 states, and I have 12 first order equations. The only problem is that these equations are super complicated and non-linear. So what I'm going to do is I'm going to take these equations and linearize these equations. And let me tell you what this linearization means. Linearization means is all these complicated equations which are written something like this. And I'm going to say f of x comma u is equal to x dot. This equation can be approximated as x dot is equal to ax plus bu, where A is a matrix, which is a 12 by 12 matrix. This is a 12 by 1. And actually, you will have the control inputs. Basically, there will be a lot of zeros here. So when you look at this equation, your control input will be delta E, delta A, delta T, and delta R. For that will be the control input, and somehow we will come up with a controller algorithm, some sort of mathematical relationship that helps us simplify. So let's keep on the price. So here is what is happening. We have this equation, and after all this mathematical jugglery, I would like to come up with this equation. And this equation is nothing but the linearization. Yeah, 12 by, this will be, yeah, 12 by 4, correct, 12 by 4. So that is correct. So ideally, after all this simplification here, so there is this test of simplification, and I want you to look at the material that we discussed in the robotics one. This is nothing but A is nothing but Jacobian of the given equations, and this Jacobian can be formulated mathematically or can be derived theoretically, but we use Simulink function. It's called as lin mod. That would help us to linearize the system approximately using numerical techniques, some optimization techniques. So now what I'm going to do is I'm going to go through these equations. Once again, don't get scared. These equations may look intimidating, but MATLAB is going to solve it, not us. So just try to understand the physics behind the equations. We have the equations in the Genesis block. So these equations are 12 state equations, and I want to write them in the form of x dot is equal to ax plus bu. So that is my whole purpose. So let's start with these equations. So we start with these super complicated equations. And here is something else I want to talk about. That even though these equations are, if you think about states, you have 12 states, 12 rows, 1 column. You have a matrix 12 by 12. You have x, this is x dot, 12 rows, 1 column, plus you have by 4, and then you have your delta E, delta A, delta R, and delta T. Now, this is what we are trying to achieve. But here is the problem. To solve this equation, their original form could be complicated. So what we can do is we can come up with a reduced order model. What is this reduced order model? What it means is we partition this system wherein we notice that the first top half equation is controlling the majority of the dynamics. So what I would do is, and I'm going to call this XR, XR, AR, and BR. So the reduced order model is rather than using whole 12 by 12 equations, we will try to pick and choose the most important equation that control the significant part of dynamics. And it is like, for an example, trying to look at which equations are the dominant equations in all these 12 equations. That is nothing but the reduced order model. And we will look at the simulation with the full scale model and the reduced order model. But the idea is we are going to start with those 12 nonlinear equations and then try to come up with some sort of simple equations and use those simple equations for our controller design. So let's start the lateral in. So if you look at the lateral states are defined over here. These are the states that govern the lateral dynamics. And please understand, these are the exact same states that we used when we derived the state space model. And if you look at the control surfaces for the lateral states, the control surfaces are aileron, rudder. So this is aileron, and this is the rudder. What I want to do is, I want to look at these equations. So I'm going to look at the equation for V dot. I'm going to look at the equation for P dot. I'm going to look at the equation for R dot, equation for phi dot, and location for psi dot. These equations come from the JS block. These complicated equations are nonlinear and coupled. So what I'm going to do is, I'm going to somehow simplify. A very simple approximation is, for an example, if I have maybe sine theta, I will approximate it to theta. If I have cosine theta, if my theta values are small, I would approximate that to 1. So basically what I would do is, I would use a Taylor series expansion to come up with the simplified expression of this nonlinear set of equations. And believe it or not, this is nothing but the Jacobian that we talked about. And this is what we have studied in Robotics 1. Remember, in Robotics 1, when we looked at the equation for position. So equation for position of the end effector, I had xp, y, zp. And then what we did is we used the Taylor series expansion and Jacobian for linear velocity, and we use the Jacobian for angular velocity. That exactly what this is all about. So wherein what we have here is we have a Jacobian, and Jacobian, if you think about it, is nothing but what we are doing is we are keeping all the state but one constant and trying to find out the effect of varying one particular state when all the states are constants. That's why these are all partial derivatives. And if you have any questions about the Jacobian, I would encourage you to take a look at the Robotics 1 video lecture. You should still have access to the Robotics 1 video lecture, where we talk about Taylor series, linearization, and Jacobian. And also discussed very detailed in the videos trim 1 and trim 2 on Canvas. So please watch those videos. They are 10 videos, but they will give you a physical understanding of what the Jacobian is. Now, when this Jacobian is performed, and to be honest with you, I don't intend to perform partial derivatives by hand. I would use MATLAB or Mathematica, some other software, to perform this partial derivatives. I land up with this equation. And this equation is the linearization of that linear equation. So this is BU. So please note, U are control input, X is the state, A is the state matrix, these are the derivatives. And please observe these terms here, they are represented as just notation, and these notations are expanded over here. So when we actually program these inside MATLAB, we will have to type in all these equations and program them inside the MATLAB environment. But wait a second, you really don't have to do that. No, we haven't eliminated any states yet. We are not at the reduced order model. But wait a second. What you can do is you can start with the equations on the Genesis block, and use the Simulink function for automatic linearization. So it means all this linearization that you see here can be done using MATLAB. That is what we will discuss in next class. Then what we do is, here is slightly a different form of the lateral equation. And the lateral dynamics, if you are going to use the side slip angle instead of velocity, so this is side slip instead of velocity, you can rewrite those equations for dynamics in terms of side slip uh, angular variation. And these equations have slightly different form, but at the end of the day, they give you all the information that you need, because VA, airspeed, multiplied by the sine of side slip gives you V. So you can substitute, you can actually use either this equation or you can use this equation to simulate the lateral dynamics. Now we are going to do the same thing for the longitudinal dynamics. Again, in the longitudinal dynamics, our equations comprise of these u, v, q, theta, and h, which is the altitude. And the longitudinal dynamics control states or control variables are the elevator deflection and the throttle change. So you have the elevator and the throttle. So once again, you have u dot over here, w dot over here, q dot over here, theta dot over here, h dot over here. These equations come from the Genesis block. And then what you do is you perform this Jacobian operation, and then you land up with these state equations. Believe it or not, these equations are similar to the equations that we found out earlier. And MATLAB is so very nice that the transfer function that we have derived can be converted to state space using the command tf to ss, or these state space equations can be converted to transfer function using the command ss to tf. So the state space representation and transfer function representation can be used for controller design, and I will try to show you design of controller using both implementation. But try to understand, at the end of the day, we have these 12 nonlinear equations and we are coming up with some linear approximations. So here is the alternative form of the longitudinal equation. Now the alternative form always uses side slip angle. So if you want to represent the dynamics with respect to side slip angle and the angle of attack, then you can rewrite these equations. These equations can be rewritten in terms of angle of attack and side slip equation that are given here. Again, it's totally up to you. Even though you use the equations in the first form or equation in the second form, it does not matter. Finally, your answers are going to be the same. As a matter of fact, if you look at some of these constants basically are the same. So that is how you can simulate the complete dynamics. But the control techniques could be different depending upon whether you are controlling in state space or whether you are controlling in the transformation. So please understand, state space is control in the Laplace domain, and transfer function, or in frequency domain, transfer function is the control in time domain. And in state space, recollect, we have poles, and transfer function, we have eigenvalues. And reduced order models. Reduced order models are used in case that we are just focusing on the part of the dynamics. And these reduced order models are constructed to focus on particular behavior of the aircraft. And there are some longitudinal modes and lateral modes that are of significant interest when we look at the reduced order model. So what I'm trying to say, what a reduced order model is, you look at those 12 equations, and out of that, you consider only maybe 2 or 3 equations to study particular mode. And that is nothing but construction of reduced order model. And it's very difficult for me to describe these motions. So I would strongly encourage you. Transfer function is controlled in Laplace domain. Oh, sorry. I made a mistake here. This is transfer function. Transfer function is controlled in Laplace domain, and state space is controlled in time domain. Yeah, good catch. So because transfer function will have S variable and state space will have T variable. Okay. Now, reduced order models is you have these 12 sets of equations. Out of that, you are going to look at a very small subset of equation to study something called as a short period mode. Short period mode means when the aircraft is in longitudinal flight, aircraft does motion something like this. That's called as the short period mode. Phugoid mode is like the aircraft is in the longitudinal dynamics, but it makes the upward and downward motion because eigenvalues are too far away, the eigenvalues are larger, the period is larger in one mode and the frequencies are smaller in other mode. So I would strongly recommend watch YouTube video describing this short period mode, Phugoid mode. These are 2 longitudinal modes that are commonly used to study the aircraft dynamics. And you can study the roll mode. There is something called as the spiral divergence mode and Dutch roll mode. So it is very interesting that when the aircraft rolls, you will see sometimes aircraft rolls like this, sometimes aircraft rolls like this, sometimes the aircraft rolls in a spiral divergence fashion. It's very interesting to see these motions in your flight simulator. So I would strongly recommend, rather than me talking about how these modes actually are, just watch YouTube videos on short period mode, Phugoid mode, roll mode, divergence mode, and Dutch roll mode. And if you are very interested, you can simulate these modes in your simulator. So basically, you can change the parameters in your flight simulator so that your aircraft can actually exhibit these different modes of dynamics. And that is something you'll be able to do after our simulation is complete. And let me quickly look at the next project. So the next project, I don't know if you started working on it or not. I would strongly recommend that if you have not started working on the project, please do so, because in next class, I'm gonna work out the problems and I will give you hints and code that will get you started. So please watch the MATLAB videos on trim and Linmon. And then what we will do is we'll use our simulation, project 3 simulation, to be expressed in either in transfer function format or the state space format. And then we will use the trim command on our project to come up with the trim states And then what we will do is we will have the equations. We will have a representation in transfer function. And then we will look at the eigenvalues are for the open loop. And then we look at the closed loop behavior. And this is something very important, this exercise, because when we go to the next chapter, which is autopilot design using successive loop closure that we just talked in today's lesson, we'll use these models to come up with different expressions. One thing I just want to clarify and make you aware, remember that you have something called as the Project 9. Project 9 is watching MATLAB videos and getting the certificate. When we look at the next lesson, we are going to talk about something called as state flow. So I would strongly encourage you to complete the MATLAB course on state flow, and I will show you where that is. So this is for the next chapter, for chapter 6. So when we look at the chapter 6, we are going to use the information on the state flow. So I would encourage you to look at the MATLAB project 9. Project 9, if you look at the assignment, I'll quickly open project 9 and I will share my screen. So project 9, this project 9 is using the MathWorks videos. So the first one is still processing on ramp. I would expect that most of you have done it by 1.6, control system 2.4, and the state flow is 2.16. And the reason I want you to do this state flow, because chapter 6, when we do the autopilot design, is going to use the state flow. So if you have done this on RAM, so I'll just take you where, copy, go to your screen, paste. It will take you to MATLAB on RAM. And then please, this is all free. So please do it. This will actually give you an idea of different type of state flow techniques, and that will be useful when we study chapter 6. It won't be used in next week, but it will be used week after next. So properly and study this material. Okay, that's it for today. I'm gonna stop recording.